All right, good morning, everybody. Those of you who showed up. So anyways, so yesterday we started talking about how Ampere's law, or Maxwell's Ampere's law, the modification of Ampere's law, along with Faraday's law, gives us light. Right? So again, it's the interaction between these two things, which gives us the wave equation, which then Maxwell then predicted light. And what he showed was that the speed of light in vacuum/air, even though it's slightly different than air, but we still call it about approximately c, is 1 over the square root of epsilon naught times mu naught, which is about 3 times 10 to the 8th meters per second. And remember back from our wave stuff, remember the speed is also equal to the wavelength times the frequency, which means that for large wavelengths, we have very small frequencies. For small wavelengths, we have very large frequencies. And this over here, I'm just pointing out, you don't have to know this part so much, but the energy of a photon, so basically the energy at which light is carrying, is equal to what's known as Planck's constant times the frequency. So as the frequency goes up, the more and more energy that the photon actually carries. So the more light carries energy. So that means for very small wavelengths, so things like X-rays and gamma rays and all that kind of good stuff, where long wavelength stuff, so radio waves, things like that, have very low energy. So they have very large wavelengths, but very small frequencies, which means that they have very large energy. So good. So speaking of waves, so remember we talked about way back when, towards the beginning of the semester, waves carry both energy and momentum. And we talked about light, knowing the fact that we actually know it carries energy. So what we're going to talk about today is how much energy that this thing actually carries. And to do that, we're going to introduce something which is called the Poynting vector. So the Poynting vector, by definition, is equal to S, which is 1 over mu naught times the electric field crossed by the magnetic field. So the Poynting vector actually tells us multiple things. The first thing it tells us is, we also mentioned yesterday, that the direction of propagation of the light is given by E cross B. So the Poynting vector actually points in the direction of propagation. So the Poynting vector, first off, tells us, number 1, the direction of light propagation. So what direction is my light actually traveling? Because this thing is proportional to E cross B. So we know that guy tells us the direction. The other thing it tells us, which usually I go through a long derivation, but usually that goes over kind of like a fart in church, basically, so it doesn't go over that well. So I'm just going to ignore that this year. It'll be the first time I'm ever going to ignore that derivation. And let's just look at the magnitude of the crossing, or the Poynting vector. So this then is equal to 1 over mu naught times the magnitude of E cross B. But as we showed yesterday, and we actually mentioned yesterday, the electric field is always perpendicular to the magnetic field, which means that's the same thing as the magnitude of E times the magnitude of B times sine and angle between the two. But since they're perpendicular to each other, that sine is simply equal to 1. So this is simply EB over mu. Now, if I go through and I actually look at the fundamental units of the electric field, the magnetic field, and mu naught, what you can actually show, which I'm going to skip that part too, is that this thing has units of watts per meter squared. So the other thing that the Poynting vector then tells us then is, remember watts per unit squared, if we go way back to chapter 17, is intensity. So this is actually equal to the intensity of the wave. So I here is equal to the intensity. So the Poynting vector also tells us the intensity. So what's the intensity? So the intensity is the rate at which energy is delivered to an area. So this is what intensity is. So basically all that means is if I have my light coming in like this, and that's going to interact with an area of A, what the intensity then tells me then is the rate at which energy is brought to this area. So this is intensity. So intensity then has units of 1 over area times the rate of change of energy. So this is intensity. So the Poynting vector tells me the direction at which my light is traveling. It also tells me how much energy it's carrying, because if I know over a certain amount of time, and I multiply that by the area, then that is the energy at which the light is carrying. So the higher the intensity, the more energy at which the light is actually carrying. Right? So the Poynting vector tells me all these different things. So it tells me the energy at which it's carrying, It tells me the rate at which that energy is being carried, and it also tells me the direction at which this light is moving. So this is what our Poynting vector tells us. Now, what we're going to be mostly interested in are signals which have high frequencies. We're going to be looking at things like light from the sun, etc., which means that if we think about the intensity, which again is equal to the magnitude of the Poynting vector, then this is going to be equal to something that goes as E0 times sine of omega t minus kx times B0 times sine of omega t minus kx, all divided by mu 0. So we're going to be looking at mostly is light which is oscillating very quickly, which means that the angular frequency is going to be very large. Right? Which means that basically this thing is proportional to a sine squared. So if I was looking at a period, so if I was plotting this thing divided by B0 E0 times mu 0, this thing would just be a sine squared. So sine squared is going to do something like this, right, over the time of a period. So it's going to be over one period. So since this thing is oscillating very rapidly, one period is going to be something very small. So you're talking like femtoseconds or picoseconds or something ridiculously small like that, right? Which means that as this thing is oscillating, we don't really notice how this thing is changing from moment to moment because it changes so rapidly, which means that most of the time we're actually going to be taking the average of this. So if I looked at a sine squared, the average of a sine squared is exactly through the middle of it, which means that the average is simply equal to a half. So most of the time we're going to be interested in is not necessarily the intensity or the magnitude of the Poynting vector, but actually the average of that. So typically we're going to call then is that the intensity is actually equal to the time average of the Poynting vector, which in this case then is going to be equal to E0 B0 divided by twice of mu naught. This is what we're going to call the time average. So again, most of our sources are going to have very high frequencies, which means that these things are going to be oscillating very, very rapidly, which means as we're trying to measure this object, we're not going to measure its value from moment to moment to moment. We're going to measure its average value. So that's what this thing is. So in this case, we're actually going to define the intensity to be this, the time average then over the Poynting vector. Or again, if this is a sine squared, the average of the sine squared is simply equal to a half. That's the average of this guy. Now from here, we can then define RMS values. So you guys remember what RMS values are? We talked about these last semester. If you don't, that's fine. So from here, we're going to define RMS values of the electric field and the magnetic field. So the RMS value is going to be equal to the peak or the amplitude of the electric field divided by square root of 2. And the RMS value of the magnetic field then is going to be the peak or the amplitude divided by square root of 2. Which means in that case, our intensity then is going to be equal to the RMS value of the electric field times the RMS value of the magnetic field, all divided by mu naught. So this is going to be our intensity. Now, what we also know is that the speed of light is related to the electric field and magnetic field amplitudes by the speed of light is equal to the electric field amplitude divided by the magnetic field amplitude. Which also means that if I divide that one by square root of 2 and I divide that one by square root of 2, this is also equal to the ratio of the RMS value of the electric field to that of the magnetic field. These things are the same as well. So another way we can actually write this then is we can write this as, so I can write this as what? ERMS squared divided by C times mu naught. So here I'm just replacing that what B RMS is equal to ERMS divided by E, or divided by C. So I'm just replacing that, which gives me the C on the bottom. These things are the same. So good. So this is then the intensity. So, okay? So let's do an example. So this example says that radiation from the sun reaches the Earth and the upper atmosphere at a rate of about 1,350 watts per meter squared. So that's our intensity. So then it says, assume that this is a single electromagnetic wave, meaning it's monoatomic or monochromatic wave, and calculate the maximum values of the electric field and the magnetic field. So we have a monatomic wave, which means there's only one frequency. So that's it, so one color. So here we just want to find out what then is E0 and what is B0. Okay? Not too bad, right? So good. So let's do that. So we're just going to use that thing I exactly wrote down. Good timing. So in this case, I have that the intensity then is equal to the Rms values squared of the electric field divided by speed of light times mu naught. And we also know again that the Rms values squared is then equal to the peak or the amplitude squared divided by 2. So this is also then equal to the amplitude squared divided by twice c mu naught. So this then says that we can find the amplitude of the electric field as then being simply equal to the square root of twice c mu naught times the intensity. So plug in our numbers, this then is equal to the square root of 2 times 3 times 10 to the 8th times mu naught, which is 4 times pi times 10 to the minus 7 times the intensity, which is 1,350. Plug in our numbers, we find in this case, this works out to be 1.01 times 10 to the 3rd volts per meter. So this is our amplitude of our electric field. To then get the amplitude of the magnetic field, we're now just going to use this relationship. Since we already know E0, we already know C, we can then find B0. So this then says that B0 is then equal to E0 divided by C. So it's going to be 1.01 times 10 to the 3rd volts per meter divided by 3 times 10 to the 8th meters per second, which makes that guy very small. So this gives me 3.37 times 10 to the minus 6 Teslas. So one thing that'll always be true, again, since the magnetic field's amplitude will always be smaller than the electric field by a factor of the speed of light. So the magnetic field will always be ridiculously small compared to that of the electric field amplitude. About 8 orders of magnitude smaller, typically. So very, very tiny. It was okay? Not too bad. So since light actually carries momentum, that means that we can actually get a pressure and a force out of light, which is kind of cool. What do I mean by that? What I mean by that is, let's say here's a wall. Okay, so here's my wall, or some sort of object that I'm going to interact with. So for now, let's just call this a wall. And then let's say I have light which comes in and then interacts with it. Okay, so here's my light coming in and hitting it. Well, we know that the light is carrying momentum, which means that it has a momentum in this direction, P. So what's going to happen then is it's going to collide with the wall. And then when it collides with the wall, it depends on the type of interaction it has with the wall. So typically, there are going to be 2 different types of interactions. I'm either going to have the wall absorb the light. So for example, if I did what? If I painted my wall black, in that case, it's going to absorb it, right? So in that case, all the momentum then will terminate on the wall. It's going to be completely absorbed. Okay? That's case number 1. So this is going to be absorbed. Which means in this case, my change in momentum then is simply equal to the initial momentum which is coming in. So in that case, I have my final momentum, which is 0, minus my initial momentum, which is non-zero. In this case, I'm talking about the change momentum of the wall itself. So in that case, it's just the opposite. Good. So, or case number 2 is I can also have the lights being reflected off of it. So in that case, I can have lights being reflected, and let's say it's completely elastic. So in that case, it's going off in this direction with the initial momentum which is coming off it. So in this case, this would happen if I painted my wall silver. So in this case, if this was silver, case number 2 then is it's going to be fully reflected, in which case then my change in momentum would then be equal to twice of the original momentum. what do we know? We know, though, that when I have a change in momentum, if that change in momentum happens over a change in time, now we're going back to physics 205, the change in momentum with respect to time is simply a force. So remember that what happens then is the wall and the photon here are going to feel a force, where that force then is equal to the change in momentum divided by the change in time. So this is just Newton's second law. Now, but if I divide the force divided by the area, then this is equal to the pressure. This is what we're going to call the radiation pressure. So the change in pressure, or sorry, the change in momentum divided by the change in time times 1 over the area then is equal to the radiation pressure. Now, it turns out that when it comes to light, the change in momentum is equal to the change in energy divided by the speed of light. That's a hard derivation to come up with. I'm not going to bother doing that. Just take my word for it for now. Okay. So good. So that means I can rewrite this guy then as what? The change in energy divided by the change in time times 1 over the area times 1 over the speed of light. Okay. Now, if I go back a couple slides, though, what we said is that the intensity is actually 1 over the area times the rate of change of the energy, which actually means that what? This quantity here, then, is actually simply equal to the intensity. So, in this case, if I'm looking at case number 1, my change in momentum then is just 1. But if I'm looking at case number 2, then my change in momentum is twice of this, which means in that case, I actually pick up a factor of 2. So if I'm talking about case number 1 then, so for case number 1, what this says then is that my radiation pressure is then equal to the intensity divided by the speed of light. In case number 2, in this case, my radiation pressure is equal to twice of the intensity, since it's greater by a factor of 2, because I have twice the change of momentum, divided by the speed of light. So in general, the way we're going to write the radiation pressure then is then equal to A, which is some constant, times the intensity divided by the speed of light, where A is going to be anywhere between 1 and 2. Where 1 is when this thing is absorbing, and then 2 when this thing is completely reflecting. Now, as far as this class is concerned, it's either going to be 1 or 2. As far as reality is concerned, it's going to be somewhere between 1 and 2. Almost nothing is fully reflective, almost nothing is fully absorbing. These are both ideal cases. This one is what we call a black body. This one then is what we call a perfect reflector, things that we talked about when we talked about thermodynamics last semester. In this case, we're going to pretend it's either a black body or a perfect reflector. So it's going to be one or the other one. So if otherwise, I'd have to tell you exactly what A is. So that's basically about it. But again, as far as this class is concerned, it's going to be either one or the other one. So what does this say? So what this says then is that when light is shining on me from here, I am feeling a pressure, which means I am feeling a force. So right now, this light shining onto me from the overhead projector is trying to push me backwards in this direction. Am I being thrown backwards because of this light? No. Why? Because I am huge, damn it. That's why. Okay. Basically, we're going to do an example of this, and you can kind of see how small this ends up being. But this force that we feel from the light constantly hitting against this, right? This thing is constantly doing this, which means that there is a pressure on here. There is a force on here. This thing is trying to push back this way. But the intensity is so small, meaning the force is so small that it doesn't actually do anything, because the intensity of the light in this case is very small. But if I had something which had a huge intensity, for example, a laser, which has a very powerful intensity. I can create one that has very powerful intensity. I can take something like a sphere, hold it over top of the laser, and actually levitate it in space. Anybody had LASIK surgery or know anybody had LASIK surgery? What do? They cut your eye open. With what? A laser. Radiation pressure. Right? So for most things, we don't have a great enough intensity. Even if I shone a laser on me, I'm typically not going to levitate myself, but I'm going to cut a hole for myself, which is kind of cool. If you have like a YAG laser or something like that, where you have to actually run water through it to cool it down so it doesn't explode, you can cut through things very nicely. You can't really levitate it, but you can actually cut through it. So for most intents and purposes, this is not a huge force that we're going to feel for large macroscopic objects like ourselves. But things that this is important for are things like DNA. We can actually create things called optical tweezers. So in that case, you take lasers, you shine them where they actually intersect with each other. You can grab things like DNA and actually physically move it around. This is why we know the length of DNA. Because you can pin it on one side with a laser, grab it with the other side and move it, and then stretch it out as far as you can actually stretch it. Other things that this is useful for are things like early universe, where you have a lot of light. You can actually cause gas clouds to be crushed in on top of each other from the light from the outside, causing huge dense overdensities of gas, which are going to create things like planets, stars, black holes, all kinds of cool stuff, right? So this has a huge effect on things which are usually microscopic. So typically things like atoms, things like molecules, things like that, you can actually manipulate them and move them around just using radiation pressure, radiation force. But again, big things like us, it's not usually going to do anything for that. I don't walk outside and all of a sudden feel crushed down because of the sun. So typically things like that, we're not going to have a lot of manipulation power over. But this can be a huge force depending on the things that I'm actually looking at. Okay? So let's do an example of this and let's see how small this thing typically is going to be. Or again, macroscopic type sizes of stuff. So this says radiation from the sun reaches the Earth's surface, transforms energy at a rate of 1,000 watts per meter squared. So at the upper atmosphere, it's about 13,000 or 1,350. By the time it makes it through the atmosphere, usually it's about 1,000 watts per meter squared by the time it reaches the surface. So in this case, we want to estimate the pressure and the force exerted by the sun on my hand. So if I went outside, put my hand in there, how much force would my hand feel downward because of this sun? Okay. So let's do that. So good. So let me draw my beautiful hand. So there's a finger, a finger, a finger, and a finger, and a thumb. There we go. Not my worst drawing ever, so not too bad. Good. So I got light coming in. My light is coming in. This has an intensity equal to 1,000 watts per meter squared. Now, for this purpose, I'm going to pretend that I am absorbing. Even though I'm so white, I'm actually reflecting, but let's pretend. So in this case, we can then say that what? Our radiation pressure is then equal to what? Simply the intensity divided by the speed of light. I'm just going to drop that factor of 2. Because I am absorbing, damn it, not reflecting. So good. So this means that my radiated pressure then is equal to what? 1,000 divided by 3 times 10 to the 8th meters per second, watts per meter squared. So, plug in my numbers. What I find in this case then is this works out to be about 3 times 10 to the -6 newtons per meter squared, right? Or pascals. So little tiny pressure. So now, if I want to calculate the force, right? So the radiation force, well, the radiation force then is simply equal to the radiation pressure times the cross-sectional area. So now we just need to guesstimate the size of my hand. Right? So let's guesstimate the width of my hand and then say the height of my hand. So that the area then is just going to be the width times the height. So let's just say that my hand is 10 centimeters wide and 20 centimeters long, just for funsies. So this then is going to be equal to our 3 times 10 to the minus 6 newtons per meter squared times 0.2 meters times 0.1 meters. So plug in our numbers, and this works out to be a force that's about, what, 6 times 10 to the minus 8 newtons. So, give you context, how much force is that? Well, the weight of my hand is probably about 2 newtons itself. So my weight of my hand is, say, roughly about 2 newtons. So how much extra force am I getting by putting my hand in front of the sun on the surface of the earth? Is that going to be a substantial force or not? No. So this is ridiculously small compared to that. So again, as far as me going outside, I'm not going to feel much force. This is not going to do much to me or to my body, right? Again, I'm not going to be crushed down because I'm out in the sun. I may complain a lot because I'm out in the sun, but that's a whole other story. I don't like being hot. So, but again, macroscopic things, this is not a huge force. But again, things like early universe or out in space where you have gas clouds, if you have it near some other astral bodies which have a lot of light, that radiative pressure could be a lot. That's going to cause all the gas to be pushed into each other, into the center, cause an overdensity, which then will create formations of things like stars, planets, etc. Optical tweezing, things like that, lasers. You can create all of these different things using this force. But again, for most macroscopic things, this is not going to be a huge amount of force. So, having said that, I'll give you a group assignment on this. I have another group assignment as well, but we'll do this one first since we're talking about this. So, another way that you can use this force to your advantage is in solar travel. So, well, it's not the one I'm looking for. Let's see here. Where'd it go? Okay, well, I guess we're going to do this one instead. So this says that someone plans to float a small, totally absorbing sphere of 0.5 meters above an isotropic point source of light, so that the upward radiation force from the light matches the downward gravitational force. The sphere's density is 19 grams per centimeter cubed, which means that's 19,000 kilograms per meter cubed, and a radius of 2 millimeters. So I want to know, what is the power required for the light source? And then even if such a source were made, why would the supports of the sphere be unstable? So we'll deal with that in just a second. So let's draw our picture. The other one I was thinking of was one that we have, you can create solar sails and actually use the radiation pressure from the sun to actually move around solar sails in space, but apparently I don't have that one, so we'll do this one instead. So here, what this is saying is we have a point source. Our point source then is giving off light in all directions, right? So this thing is doing this, so that this is our radius of R, okay? And then what you're trying to do then is take a little sphere here at the radius of R and then float this guy so that you have a radiation force in this direction, F radiation, and then you have a gravitational force pointing downward. And what we want here is that the sum of the forces is equal to 0, so that this thing is floating. So, things to pay attention to here is, since this thing is an isotropic source, what that means then is what? When you're trying to calculate the intensity, you need the fact that the intensity goes as 1 over the area of the entire sphere here. Right? So this is something we talked about way back when. What we said was that the intensity was equal to the power divided by the area, which in this case then is equal to the surface area of the sphere. Which means in this case, this is equal to the power divided by 4 pi r squared. So this is how you're actually going to get the power. So this is where the intensity part comes into. But so here we're going to have that the radiation force is then equal to mg, where the radiation force is equal to, since it's absorbing, the intensity divided by the speed of light equal to mg. Now here, mg, I gave you the density of the object and then the radius of the object as well. So you just have to figure out the mass from there. So that'll be our first group exercise. I'll let you guys work on that. Most of it's already set up, so you can just have fun from there. Or if you want, you can call this one capital R. So that you can call the radius of this guy little r. In that case, let's just make that a capital R. Whichever it is that you fancy. Doesn't matter. So, give you about 10 minutes to work on that one, and then we'll talk about the next one. Go back to the slide? Yeah. Sure. And this is already up on Blackboard. I think I put it up on yesterday, but. And I graded your exams, but I forgot to bring them with me, so you'll get them tomorrow. I apologize. Yeah. What's that? Better than the first two exams, but not quite as good as the last exam. So it was a little above a 60 from what I remember. Not too bad. Better than the first two. So that's good. Cool. I was in a mad rush to make it to the gym before I made it to class this morning. So. Everybody was driving 2 miles an hour this morning. Oh, boy. It's horrible. There's so much traffic, too. Usually it's like clean all the way through here. Right. Like nobody wanted to get out of bed, and then they're all doing 20 miles an hour.
I did a lot better than what I thought I was going to be saying. Like, I know the average, but like, I like just didn't answer for you because I didn't have time. Like, I was thinking, so like, I have such better grades because I knew that name. Didn't have that.
I saw your little note on there.
I was so frustrated with myself because it was like the first part, I knew how to do the whole entire problem. And I was like, this is going to take me too long in part C, so I was like, I'll come back with
nothing.
Same thing happened in part 2. I think it was a big crap. It was just like one thing after the other.
Cascading.
And like I literally did the short answer problem thing, so we had like 5 minutes left. Because I was like, oh no, like I gotta do these two.
During exam, every time I open my mouth, Corey loves giving me a dirty look. Maybe you don't feel me. Yes. Remember that, yeah, 1 gram per centimeter cubed is 1,000 kilograms per meter cubed. It should be, yeah, because the radius is pretty small, right? Yeah, 2 millimeter radius. So you don't want something too heavy, otherwise you need much more power.
I was thinking that it was really,
And so 4/3 times 19,000 times 0.002 cubed.
Should I just change the radius of the sphere to centimeters since it's in grams per centimeter cube?
If you want to do that, but then you'll have to change grams to grams to kilograms. Either way, when I do it's fine. Yeah.
But then if I want to try to change this to centimeter cube, meters cube, right?
Well, like I said, it depends on how you want to do it. So you could. So to turn that one into kilograms, so that's going to be 0.019 kilograms per centimeter cubed, and then put that into centimeters, and then do it that way. So that's one way. But ultimately, you get the same answer at the end of the day. I got different answers for unit conversions every day.
Yeah.
Yes, that are the 0.5 meters. Yes.
Wow. Change your green.
What you mean by that? So yeah, keep that. The power over surface area?
Yeah.
That's intensity. Yeah, so that's watts per meter square. So, units wise. All right, so let's bring up the next one. This actually has to do with stuff we were talking about yesterday. So all the displacement current stuff. So let's talk about this guy, and then I'll give you the rest of the time to work on this, the other one. So it says the magnitude of the electric field between two circular plates is time dependent, which in this case is given this way. So it's a constant minus something which is time dependent. So the electric field is 4 times 10 to the 15 minus 6 times 10 to the 4 times the time. And it says that t is equal to 0. The electric field is pointing upward, as drawn in our picture. So these are my circular plates. The plate has an area of 0.04 meters squared. For any t larger than 0, what are the magnitude and direction upward or downward of the displacement current between the plates? And C is the direction of the induced magnetic field, clockwise or counterclockwise. So let's remind ourselves of displacement current. Let's bring that guy back up. So remember, displacement current is equal to epsilon naught times the rate of change of the electric flux, which again is equal to epsilon naught times the time rate of change of the integral of the electric field dotted by the differential area. Now, in our problem here, does it say anything about the electric field being anything other than time dependent, meaning is it spatially dependent? No. So we're going to assume it's spatially constant, which means that this thing is just going to become epsilon naught A d dt. So in this case, you're just starting off with this. Okay, so this is your displacement current. So this is going to give you the magnitude of the displacement current. Okay. Now the other part, it wants to know what's the direction. Well, remember that the displacement current goes in the direction of the change, not opposite to the change, but the direction of the change, which means that if your electric field is increasing, you induce an electric field in the same direction as the external electric field since it's increasing. If it's decreasing, then you induce an electric field in the opposite direction of the external electric field to enhance the change. Right? So you're always trying to enhance the change instead of decrease the change. So that's how you answer then part D. And then once you know the direction of the displacement currents, i.e. the direction of the induced electric field, your fingers then will go around in the direction of the induced magnetic field. So that's how you're going to look and figure that one out. Okay. So that's all you need for those. What's up? What's the answer to the first big box?
Yeah, the first group is on the other one.
Oh, the other one. Gotcha. That was a good question. Oops, okay. It was something like 10 to the 11. Not much I remember. Yeah, 4.68 times 10 to the 11. So tomorrow we'll start talking about polarization of lights. So how is light actually polarized? Turns out light is typically polarized in one of two ways, either linearly polarized or circularly polarized. We're only really going to talk about linearly polarized. And then what happens when you send it through polarizers? How does the polarization change? So we'll talk about that tomorrow. And then we'll be done with this chapter. That would be great. Then we'll start other stuff, more easier stuff. So where's yours? Okay, so there's the I and top and bottom. Good. Okay. Oh, because it's 19,000, not 1,000.
That's still intensity, it's not power. So it's still an I. We have reached power.
Right. Good.
And then the power.
Oh, I see. Okay. No, you put that back. Yeah.
So there we go. And then your processor whatever you use as pi r squared. What was it called? You got the wrong number.
It's 4 minus, right? Yeah.
And then times 0.5 squared. Times 4 times 5. And then times 3 times 10 to the
Huh. Okay. What'd you get?
You got to say that shit.
Okay. Maybe I'm just wrong.
Yeah.
It's
That's what they got.
5.8 times 6.
Okay, so for the previous problem, it might be 5 times 10 to the 6. I'm not sure. I'll double check
Your power is
I'll go through and check that. Oh, I see. Okay. So that should be 1,000. I just.
unproductive member of society. Yes.
Oh, 4 times pi times 10 to the minus 7. Oh, no, epsilon. Sorry. Epsilon is 8.85 times 10 to the minus 4. I guess you should use too many.
I mean, I'm done by the so I get to calculate here. I just realized my circuit final and my cap final are on the same day within an hour of each other. But I then I get to study this one though. And then I'm done.
There you go. Doing anything exciting for Thanksgiving?
Going home, get some beer.
Nice.
I mean, my parents were scared because when they were 18, they were allowed to buy meat. Chili.
Chili.
Yeah, the chili supper.
All right, so I guess we're officially done. So I'll see everybody tomorrow. Like I said, we'll start polarization. We'll go through that. We'll be done with this chapter. Do another group assignments, and then we'll probably start the next chapter. So everything from here on out is a lot easier. What's that? Yes. Huh, so it acts like your quarter wavelengths. So it turns it into,
It goes like this.
oh, it just rotates?
Yes.
So it doesn't make it rotationally. Okay.
So I can
And so
like
like,
find you all.
you have particle centers and they're like exact opposite of them. One goes this way and then the other configuration goes this way. It's really good.
Nice.
That's all I know.
Nice. See you guys tomorrow. All right.